welcome to this section of the course. Here we'll be discussing how to find the second derivative and how to use the second derivative to find sections of the graph that are labeled concave, sections of the graph that are labeled convex, and point of inflection. Now, it's quite an interesting topic, the fact that because it's applied in optimization theory, and uh, let's just start discussing by which section of the graph is convex. Any section of the graph where you can join it by any 2 points with a linear line and the line goes above the graph is called a convex. Now, the fact that it's convex means that the gradient is always increasing at any section of the graph. So, if, for example, you take these gradients here and think about it, the first gradient on the left side is more negative than the uh, appearing on the right of it. And if we label them with some arbitrary numbers, I'm not saying these are exactly the gradients, but it will form a sequence that is -100, -50, and so on. And at the minimum point, this point of the where gradient equals to zero, that's the turning point. Okay, and uh, many examples in real life where you have to find the real turning point. This turning point is minimum or maximum, and you don't have access to the graph at when you differentiate and find these turning points. So how can you know it? Well, you did briefly out at the end of the year that when the second derivative d square y dx square, the second derivative that's bigger than zero, okay, at that point you will know that the point is a minimum, right? And this is the reason for it, okay? Because the second derivative, okay, is increasing. Okay, the gradient is increasing, the rate of change of a gradient is positive, okay, as these arbitrary numbers are increasing in the sequence, okay. So the rate of change of the gradient is given by the differential of the gradient function, so the second derivative, right? So let me get rid of my handwriting here. This interval was labeled convex. We call this a convex function in this interval. So in the next section, we have concave part of a function where any 2 points joined by a straight line, and this line falls below the graph. Okay, so and you can think of the shape of the graph is taking a cave shape. So that's what I associate with concave rather than convex, is that it's like the entrance of a cave, right? So in this section, the gradient is the gradient of the gradient or rate of change of the gradient is decreasing. If you plot these uh, lines, the first one is positive, the next one is zero, and the one on the right side is negative. So this sequence in numbers where positives goes to negative, this sequence is decreasing. So the gradient is decreasing itself. So the second derivative, the rate of change of the first derivative is called the second derivative, as is denoted by d square y dx square. Okay, or in other times you might see in other books f double dash. That is also another notation for the second derivative. Okay, so these are the conclusions we come with. So there must be at some point in the graph that we passed that you have a point where the graph changes. For example, in this section of the graph, this is the convex part, and so this is the convex part, and it changes to a concave. There is a point somewhere along here, I don't know where it is, but there must be a point where this change occurs. Okay, the point where this change occurs and the graph turns from a convex into a concave function. I haven't spelled these words properly, my apologies, but is called the point of inflection. Okay, so we're going to actually figure out what this point of inflection is. Okay, and that's where in the concave section, this point of inflection is where the second derivative, I'm not going to spoil it, I'll tell you in a minute. Let's look at this example. So this question is asking us to find the interval where the function is concave. So we can find the first derivative. The derivative of x cubed is 3x squared plus 4. And we differentiate this one more time. And this is 6x. Now, for which values of 6x, we said the concave part is where the gradient is the second derivative is negative. So how can 6x be negative? Well, the 6 is positive, so the value of x must be negative. Any value, we can solve this inequality for x, and we say, well, when is it negative? When x is negative. So that's the interval where the graph will be concave. Okay, so we know that the stationary point also is where the first derivative is equal to 0. And if we check the graph out, we'll see exactly that on the left side of the y-axis, the graph is concave, although it's not quite only 2 points. The straight line falls below the curve. And on the right side, the straight line would fall above the curve. It looks like it's a convex function on the right side. So the next part of the question, let's delve deeper. Let's see. Same graph again. This next example is saying show that the function e to the power of 2x plus x squared is convex for all real values of x. So that means we have to find the first derivative and then the second derivative. So once we find the first derivative, it will be 2 times e to the power of 2x plus 2x, and we differentiate that one more time. And what we notice is that 4e to the power of 2x plus 2, if we plot its graph, it's always above the y-axis. So f double dash, or the second derivative, is no matter what the value of x you substitute there, negative a million will make it very, very small, but will not let it go towards 0. In fact, if I plot the graph here, it will always have an asymptote of 2. Okay, so this line y equals to 2 is the asymptote of the curve, and the x-axis lie here. So this line here is called the horizontal asymptote. Okay, so that's why the second derivative is always positive, therefore the graph is always convex. Okay, if we draw it, okay, the original graph is, well, I'm not going to draw that, but I'll show you briefly why it's always positive. So e to the power 2x is always positive, and multiplying it by 2 will leave it as multiplying it by 4 will leave it as a positive number, and adding 2 will always leave it as a positive number. Therefore, it's always positive, and therefore always convex. Alright, and this is what the original graph looks like. At any 2 points, the straight line joining those 2 points on the graph will be above the curve. Right, so let's discuss the point of inflection now. We said graph changes from concave to convex, or other way around, from convex to concave. There must be a point where the second derivative changes from an increase positive value to a negative value. So in this section, in this example, it is asked of us to show that the graph is concave between in the interval from -2 to 0, including those values. That's square brackets mean. It means that the -2 is included and the 0 is included. That means the equality sign applies. That's what the meaning of square bracket is. And it's convex on the interval from 1 to 3. And I've taken this graph, I've put it into Desmos. You can also use it's a graphic calculator online. It's for free. You can just sign up and use it for free as you wish. So if we start tackling this problem by finding the derivatives of the function, let's see what we're going to get. Okay, so the first derivative is going to be 3x squared minus 4x minus 4, and we differentiate that one more time with respect to x again. We'll end up with 6x minus 4. And if we substitute the value of -2 and 0, let's see what we're going to get. -2 will give us -16, and 0 will give us -4. So the second derivative is negative, right? And that will tell us that it's a convex function. Concave function, my apologies. Concave. So basically, somewhere between -2 and 0, so from this part of the graph to this part, it's definitely a concave graph. Okay? And next, we are going to use the same derivative, the second derivative that we find here, and we're going to substitute 1 and 3 into that expression. We don't have to rewrite the first derivative and second derivative again. We can just use this expression, and if we substitute the value of, let's rewrite 6x minus 4 and substitute x equals to 1, we'll end up with 6 minus 4, which is 2, and that's certainly a positive number. And when x equals to 3, we'll end up with 18 minus 4, which is again another positive number. And in this section of the graph where 1 to 3, somewhere along here, the graph seems to be definitely a convex graph, okay? Because the second derivative was shown here to be positive. Okay, now we get to part B of this question asking us to find the point of inflection, and that is when the second derivative of the function dy by dx squared is equal to 0. That means that 6x minus 4 must equal to 0. Where is that going to be? X is going to be 4 over 6, which is 2/3. Okay, and if I look at this graph here, somewhere along this line here, where this is 0, that's x value is 1 here. So somewhere along this line, I'm not sure exactly where, somewhere here is the point of inflection. That is the point of inflection. The meaning of point of inflection is derivative is equal to 0. Okay, the question is asking for the coordinate of the point, so I'm not quite finished because we did find the x value. X value is 2/3, but we didn't quite find the y value. We need to substitute this value of 2/3 back into the original function. Where is the original function? Here, on top of the page here, we need to figure out what the y value is. So we need to substitute it back there, and we get 47 over 27. So this is the final answer that we were looking for.